Hello, and welcome to my presentation over User Datagram Protocol, or UDP. What exactly is UDP? UDP is User Datagram Protocol. It is a Layer 4 transport protocol as defined by the OSI model, and it is one of the oldest network protocols in use. It is the alternative to TCP, Transport Control Protocol, which both of these run on top of the Internet Protocol to perform their functions. UDP is a connectionless protocol that is not reliable, unlike TCP, which has to be because it is used by most Internet resources. UDP uses less system resources and avoids delays that TCP is prone to. This makes UDP much faster than TCP. This is accomplished by several means. The UDP header is fixed at 8 bytes versus TCP, which can be up to 60 bytes of data. UDP is a simple transmission model that does not require error checks against the data it sends. The packets are not ordered when they are sent to the destination, as well as it uses they are sent to the destination and is not dependent on all of the datagrams having to make their way to the other side, because it does not need to verify a return circuit or to perform any checks against whether the data is lost after sending the information. This allows it to bypass the processes on the network interface. These factors help to keep the bandwidth and latency minimal in relation to TCP, which has to verify that each packet has been delivered in order with no missing or corrupted data, all while making handshake protocols all the way to the end destination. TCP is also dependent on host-to-host connections, where UDP is a process-to-process connection. All of the data sent by UDP is referred to as datagrams instead of packets. It does not divide messages into packets to be reassembled at the receiving end, or have to prepare them on the sending end. The data is not all grouped together in the datagrams, where in packets you would have a large quantity of information contained within. UDP assists in data transmission of TFTP, which is Trivial File Transfer Protocols, RTSP, Real-Time Streaming Protocol, SNP, Simple Network Protocol, and DNS, Domain Name System Retrieval, all of which are able to tolerate its lossy nature in favor of getting information quickly. It is optimal when there is a lot of data that needs to be sent and received rapidly. This fact also makes it vulnerable to attack. The connectionless nature of UDP makes it possible that it could be used to perform a flood attack on the receiving end of a network. An attacker could use this function to send out feelers on different ports until they find an open one. With the port found, they can then send a barrage of datagrams that cause a return message that the destination is unreachable. With enough of these transmissions, they can overload and crash the system. The more of these datagrams that are sent means that you will have less and less processing power as the end target struggles to keep up. To defend against this, you can monitor your UDP transmissions along with filtering which ports are allowed to transmit UDP after the attack has happened. You'll have a better idea of which ports you need to close off and which ones you need to allow access to. The differences between TCP and UDP are that we have a little bit more in-depth look between these two protocols. TCP is a connection-oriented protocol that tracks all of the data sent and requires acknowledgement that the packet was received correct and intact each time. It does this every time it performs a handshake protocol on every interface it comes across, which is very, very time consuming for all intent purposes. UDP does not require these checks, and because it's a connectionless protocol, the applications that utilize it are ones that do not need to receive all of the datagrams in order, or that they can handle there being a duplicate datagrams included, or all of the datagrams are present in the delivery. All that they depend on is that enough data is sent to carry the information as expediently as possible with the least amount of delays possible. Specifically, UDP is great for sending routing protocol updates out to different routers, which are not very large in nature. They also require less overhead to be sent, rendering the use of TCP unnecessary. It is also very handy in situations that use one-to-many multicast applications, such as when you need to push out policy updates to all the host devices on your network. TCP is more widely used over the Internet rather than UDP because it is a requirement that there is a constant communication from the host to the end and vice versa. TCP has to send information requests out that prompt a return packet that includes the information that makes up the web pages from the web server. If you tried to use UDP in either direction of the scenario, it wouldn't work because the request would be garbled and return an error message not much unlike what's shown on the screen. TCP is reliable because it creates two-way communication between itself and the end destination, where UDP sends out packets rapidly that do not require a response or acknowledgement of receipt. Another way TCP achieves packet fidelity is it sends each of its packets through the same route every single time with the same type of error checks at each point. UDP sends its packets on any or all pathways that are available along its path to the end destination. If the receiving destination host is off during a TCP transmission, it will eventually time out. Once it is timed out, it sends an error message back saying that it has reached a timeout. UDP sends its data out, and if the data isn't received, it just simply isn't received. Obviously, you wouldn't use UDP if reliability is a big concern, and would only use it if speed with minimal latency is the main goal. Video chats and online messengers all use UDP because they depend more on the fact that what is being sent is more coherent than if all the data arrives. And an example of this is sometimes, say, when you're using FaceTime or Skype, the picture might drop out or hang up for a few minutes or so, but the overall transfer of information is ongoing, meaning you're still hearing the person on the other end. You can kind of see what they look like in their movements. It may not be the clearest signal, but it's there. This is an example of UDP running like it should, despite the fidelity of the video. And The reason it would be looking like that, it would be losing some of the datagrams in the transfer. UDP is also used for online video games where packets can be dropped in favor of overall performance of the program. There might be a few times when your online avatar glitches somewhat during gameplay, but you are still online and playing, which is the important part. UDP is good for this type of transmission because it uses bandwidth and latency more efficiently to make sure that the data is as quick as it needs to be. The data can be lost as long as the connection is consistent with the data being sent. It also provides port numbers to help differentiate user requests, and because you don't need the error checks, the bandwidth load is seriously reduced. UDP is generally used for simple type communication applications that have less data attached into each datagram, like for multicasting data packets through data switching. RIP uses UDP to update routing protocols rapidly on networks so that new pathways can be discovered and configured in the less amount of time possible. The lack of flow control, error checks, and handshake protocols are why UDP is useful for all of the applications listed above, plus the ones I listed at the beginning: NTP, DNS, DHCP, TFTP, RTSP, and OSPF. All of these applications have enough data being sent via datagrams that the loss of a few packets won't affect the overall data exchange. DNS applications use UDP over TCP because when sending a DNS request, you want to reduce the load on the DNS server. Speed is more important in this instant over making sure that the whole packet is intact at the end. Because UDP is quicker and doesn't require the packet checks, it's very useful for multiple small queries that would be coming into the DNS server. This helps to reduce the bandwidth considerably, especially with a high volume of queries would be incoming into the DNS server. And in the end, if a datagram is lost in the DNS request, then another request can be sent just as fast. In conclusion, UDP, although not as reliable as TCP, has its place in the transport layer, helping to push out mass policy updates, ripping new network routes, and generally making some of the features that relate to the Internet of Things possible. Thank you for watching.